the foundations of classical physics. Throughout the annals of science, few breakthroughs have reshaped our understanding as dramatically as Isaac Newton's articulation of the laws of motion and the principle of universal gravitation. These revolutionary revelations not only transformed the study of the natural world, but also established the groundwork for classical mechanics, a scientific structure that would influence thought for more than 3 centuries. Newton's concepts remain critical for comprehending phenomena ranging from planetary paths to rocket propulsion. The tale of Newton's breakthroughs is often illustrated by the enduring image of him resting beneath an apple tree, watching a fruit tumble to the earth. While this story has likely been simplified over the years, it symbolizes the depth of Newton's inquisitiveness. Born in 1642, Isaac Newton was a mathematician, astronomer, and physicist dedicated to resolving the fundamental mysteries of motion and interaction in the cosmos. At that time, humanity lacked a comprehensive explanation of the forces controlling motion, both on Earth and in the heavens. According to popular accounts, Newton once witnessed an apple fall directly to the ground, prompting him to wonder why it descended vertically instead of sideways or at an angle. This ordinary event triggered a cascade of reflections that ultimately led to a defining moment in scientific history. Newton discerned that the same force pulling the apple downward must also be responsible for the moon's path around the Earth. This realization became the cornerstone of his gravitational theory. Prior to Newton's era, thinkers had presented various notions regarding motion, but these lacked a coherent mathematical model. Newton's laws of motion, introduced in his influential publication Philosophiae Naturalis Principia Mathematica in 1687, formed a thorough framework describing how forces influence the behavior and interaction of objects. These laws remain central to classical mechanics. Newton's first law declares that a stationary object will remain stationary, and an object in motion will persist in that motion at constant speed and direction unless acted upon by an external, unbalanced force. Known as the principle of inertia, this idea challenged the long-held Aristotelian belief that moving objects naturally stop unless continuously pushed. Newton's insight revealed that without interference from forces like friction or gravity, objects would perpetually move in a straight path. Consider sliding a hockey puck across a perfectly smooth, frictionless surface. It would glide endlessly unless something like a stick or barrier intervened. The second law outlines how an object's velocity changes when subjected to a force. It states that the force applied to an object equals its mass multiplied by its acceleration. This mathematical relationship between force, mass, and acceleration forms the backbone of our understanding of motion under influence. For example, pushing a shopping cart and a car with equal force results in the cart accelerating more rapidly due to its lower mass, precisely what this law predicts. Newton's third law proclaims that for every action, there is an equal and opposite reaction. This rule governs all object interactions, whether by direct contact or at a distance. When you press your hand against a wall, the wall exerts an equal force back on your hand. Even if the wall doesn't move, that opposing force still exists with equal magnitude. Together, these three principles became the structural core of Newtonian physics, allowing scientists to forecast how objects behave under various influences. Whether analyzing a vehicle's motion or a planet's orbit, Newton's framework enabled highly accurate predictions. While Newton's motion laws clarified object behavior, it was his formulation of gravity that revolutionized how we perceive the cosmos. He proposed that every object in the universe attracts every other object, and that the strength of this attraction, called gravity, diminishes with the square of the distance between them. The radical nature of Newton's gravitational law lay in its universal scope. It applied not just on Earth, but to all celestial bodies, moons, planets, and stars. Newton connected terrestrial phenomena with cosmic motion, demonstrating that the force causing apples to fall is the same force guiding planetary orbits. This sweeping insight united the mechanics of Earth and the heavens under one universal doctrine. His contributions transformed cosmic understanding, explaining orbital mechanics, projectile paths, tidal patterns, and more. Newton's system paved the way for future advancements in physics, including Einstein's work on relativity and the development of quantum theory. Practical applications of Newtonian physics have been just as significant. For instance, mastering motion and gravity principles made innovations like space travel and satellite communication possible. When astronauts first landed on the moon in 1969, it was Newton's laws that underpinned the calculations and engineering that enabled the mission. Modern spacecraft and launch systems still rely on these timeless rules. Despite their success, Newton's laws were eventually refined by 20th century discoveries. Albert Einstein's general theory of relativity offered a broader explanation of gravity, especially in extreme environments like those near black holes or at near-light speeds. Nevertheless, Newton's laws retain exceptional accuracy in everyday and engineering contexts. In conclusion, Isaac Newton's formulation of motion laws and universal gravitation stands as one of science's most remarkable intellectual triumphs. By integrating prior knowledge with his own observations, Newton deciphered nature's workings and crafted a model that still guides physical understanding today. From falling apples to planetary dynamics, his legacy continues to shape modern science, serving as a cornerstone in disciplines from mechanical engineering to interstellar exploration. Unveiling the science of heat, the birth of thermodynamics. As the modern world began to take shape, scientists grew increasingly intrigued by the mysterious connections between heat, mechanical work, and energy. The advent of the Industrial Revolution ushered in powerful new engines that burned fuel to produce motion, propelling ships and powering factories. However, despite their expertise in building these machines, engineers and researchers couldn't quite explain why certain engines were more efficient than others. This mystery sparked a transformation in our understanding of heat, a revolution now known as thermodynamics. The journey begins in the early 1800s with a French engineer named Sadi Carnot, who is often credited as the pioneer of thermodynamics. Nicolas Léonard Sadi Carnot aimed to enhance the performance of steam engines, the driving force of the industrial age. At the time, heat was still thought of as a sort of invisible fluid that transferred energy between objects. In 1824, he published a modest book that introduced the theoretical model of a perfect engine cycle, now called the Carnot cycle. Although Carnot lacked the complete modern grasp of heat and energy, his inquiries laid a crucial foundation. He raised pivotal questions. Why can't an engine be perfectly efficient? Where does the lost energy go? Carnot's questions motivated other scientists to investigate more deeply. Figures like Rudolf Clausius, William Thomson, Lord Kelvin, and James Joule took his ideas further and ultimately formalized the laws that define thermodynamics. They came to understand that all forms of energy follow fixed principles, principles that apply to everything from boiling a kettle to burning stars. The first law of thermodynamics declares that energy cannot be created or destroyed, only changed from one form to another. This concept, known as the conservation of energy, was solidified by James Joule in the 1840s. Joule carried out a straightforward yet ingenious experiment. He tied weights to a rotating paddle submerged in water. As the weights descended, they spun the paddle, stirring the water and causing a rise in temperature. From this, Joule concluded that mechanical energy from the falling weights had been converted into heat energy in the water. This insight was revolutionary. It showed that energy behaves like money. It can be saved, exchanged, and spent, but never destroyed. Whether it's chemical energy in fuel, thermal energy as heat, or kinetic energy in motion, all forms are interchangeable, but the total amount remains unchanged. Rudolf Clausius advanced the field even further with the second law of thermodynamics, which states that every energy conversion increases entropy or disorder in a closed system. In the 1850s, Clausius gave this principle a mathematical foundation, revealing that although energy is preserved, it naturally becomes more dispersed. For example, consider an ice cube in a warm room. The heat from the surrounding air flows into the ice, melting it. According to the second law, heat will always move from a warmer object, the room, to a cooler one, the ice, not the other way around. The melted ice, with its more randomized molecular structure, reflects a higher entropy state. This law also explains why time seems to flow in only one direction. Your coffee cools down instead of reheating itself, and a shattered egg never reassembles. Entropy increases, showing us the one-way arrow of time. Later in the 19th century, scientists uncovered the third law of thermodynamics, developed by Walther Nernst. This principle states that as a system's temperature nears absolute zero, 0 Kelvin, or negative 273.15 degrees Celsius, its entropy, or disorder, approaches a minimum. At this ultimate low temperature, a system would be perfectly ordered with no random particle motion. While absolute zero is theoretically possible, it is unattainable in practice because it becomes increasingly difficult to extract the last traces of energy. This law proved essential in understanding matter at extremely cold temperatures and paved the way for research in superconductivity and quantum physics. Curiously, the zeroth law of thermodynamics, though more fundamental, was formalized after the others. It states that if two systems are in thermal equilibrium with a third, they are also in equilibrium with each other. This transitive property allows us to define temperature consistently and to build reliable thermometers. Without it, comparing temperatures would be haphazard and inconsistent. These thermodynamic laws are far from abstract. They form the backbone of how we use and interpret energy in everyday life. They explain why engines require fuel, why refrigerators stay cold, and why chemical reactions unfold as they do. Thermodynamics touches everything from the spark of life to the inner workings of stars. Without these principles, we couldn't comprehend how car engines function, how turbines generate electricity, or even how our bodies convert food into energy. Thermodynamics also provides insight into the universe's distant future. According to the second law, entropy in the cosmos is continually rising, indicating that the universe is headed toward a heat death, a state where energy is so evenly spread that no work can be done. In this far-off scenario, stars will have exhausted their fuel, and matter will be thinly distributed in an endlessly cold and dark expanse. From its humble beginnings in the analysis of steam engines to its pivotal role in understanding the fate of the cosmos, thermodynamics is a cornerstone of science. It teaches us that although energy is constant, it spreads out over time, driving complexity, powering life, and shaping the unfolding narrative of the universe. The unification of forces, the emergence of electromagnetism. The narrative of electromagnetism unfolds in the early 1800s, sparked by a seemingly modest yet revolutionary observation. Electricity and magnetism, once thought to be entirely separate forces, are actually interconnected components of a single underlying phenomenon. While this concept is widely accepted today, it was a groundbreaking realization for scientists at the time, dramatically altering our understanding of the natural world. In 1820, a Danish scientist named Hans Christian Ørsted was delivering a lecture on electrical phenomena when he noticed something peculiar. As he moved a compass close to a wire conducting electric current, the needle shifted direction, an odd occurrence considering compass needles typically respond only to magnetic fields. Ørsted's simple but enlightening experiment unveiled a remarkable truth. An electric current can generate a magnetic field. This discovery marked the birth of the scientific field we now call electromagnetism. Before Ørsted's experiment, electricity and magnetism were regarded as distinct. Electricity involved the movement of charges observed in lightning or batteries, while magnetism was associated with natural materials like lodestone. Ørsted's findings hinted at a hidden link between the two, igniting a wave of curiosity among scientists globally. Among those inspired was Michael Faraday, a British experimentalist who took Ørsted's initial observations to new heights. Faraday was deeply intrigued by the relationship between electrical and magnetic forces. In 1831, he made a historic breakthrough. He discovered that moving a magnet near a coil of wire could create an electric current within that wire, a phenomenon now known as electromagnetic induction. To visualize Faraday's concept, imagine sliding a bar magnet back and forth through a wire loop. This motion alters the magnetic field in the surrounding space, which in turn induces an electric current in the wire. This principle became the foundation for generating electricity and led to the development of devices like electric generators and transformers. Faraday's insight revolutionized technology. If magnetism could produce electricity, then electrical power could be harnessed, distributed, and applied in unprecedented ways. His work laid the foundation for an era of electrification that powers cities, homes, and industries to this day. While Faraday made the essential discoveries, it was Scottish physicist James Clerk Maxwell who formulated a comprehensive theoretical framework. Working in the mid-19th century, Maxwell brought together the discoveries of Ørsted, Faraday, and others into a single cohesive model. In the 1860s, he presented a set of four mathematical expressions, now famously known as Maxwell's equations. These equations describe how electric and magnetic fields interact with one another and travel through space. Maxwell demonstrated that a changing electric field can produce a magnetic field, and a changing magnetic field can induce an electric field, resulting in a self-sustaining oscillation, a wave. This phenomenon is what we now understand as electromagnetic waves. Maxwell's most profound revelation was that light itself is an electromagnetic wave. This meant that visible light, radio waves, X-rays, and other forms of electromagnetic radiation are all part of a continuous spectrum. This breakthrough united the separate domains of optics, the study of light, and electromagnetism, creating a unified framework that fundamentally reshaped physics. The real-world applications of electromagnetism are vast. Faraday's discovery of electromagnetic induction directly led to the invention of generators and transformers. These devices rely on the principle that moving a wire through a magnetic field can convert mechanical energy into electrical energy, a principle that underpins virtually all modern methods of power generation, from fossil fuels and hydroelectricity to wind and solar. Electric motors, another crucial application, work on the reverse principle, converting electrical energy into mechanical motion. These motors operate through the interaction of electric currents and magnetic fields, producing rotational force that powers everything from kitchen appliances to massive industrial machines. The understanding of electromagnetic waves also paved the way for a revolution in communication technology. In the late 1800s, German physicist Heinrich Hertz experimentally confirmed the existence of radio waves, validating Maxwell's theory. Soon after, inventors like Guglielmo Marconi developed practical methods to transmit signals wirelessly, leading to the creation of radio. Radio waves, microwaves, and later optical fibers made long-distance, instantaneous communication a reality. Electromagnetism's importance extends far beyond human inventions. It is a fundamental force of nature that governs the physical world. It shapes the Earth's magnetic field, which shields life from harmful solar radiation and governs the bonds between atoms, forming the basis of matter. For instance, electrons orbit atomic nuclei due to the electromagnetic attraction between the negatively charged electrons and the positively charged protons. This force holds atoms together to create molecules and ultimately all visible matter. Natural phenomena such as auroras, the northern and southern lights, are vivid displays of electromagnetic activity. When charged solar particles strike the Earth's magnetic field, they spiral along the field lines and collide with atmospheric molecules, emitting colorful lights in green, red, and blue. These spectacles offer a glimpse into the unseen but immense power of electromagnetism. Electromagnetism is not just a scientific concept, it is one of the core forces that underpin the universe and our technological society. From its accidental discovery in a classroom to its central role in modern life, electromagnetism has transformed the human experience. It powers our homes, fuels innovation, and shapes our comprehension of both matter and light. Today, scientists continue to expand on the work of Ørsted, Faraday, and Maxwell. The development of quantum electrodynamics, QED, a theory that merges electromagnetism with quantum mechanics, has led to a more refined understanding of how particles interact. As we delve deeper into the mysteries of this fundamental force, it's evident that electromagnetism will remain at the forefront of scientific discovery and technological progress for generations to come. Unlocking the atom, Rutherford's groundbreaking gold foil test. At the dawn of the 20th century, physicists were determined to unravel the mysteries of atomic structure, an enigma that had perplexed scientists for generations. At the time, the most accepted concept was the plum pudding model, introduced by J.J. Thomson following his 1897 discovery of the electron. According to this theory, the atom resembled a sphere filled with positive charge, in which negatively charged electrons were randomly embedded, similar to raisins scattered throughout a pudding. This widely embraced model, however, would soon be upended by a single experiment, an investigation that would become one of the most significant milestones in modern physics: Ernest Rutherford's gold foil experiment. During the early 1900s, atomic research was entering a phase of intense experimentation. Scientists were aware that atoms contained both positive and negative charges, but how these components were arranged remained a mystery. Thomson's plum pudding model, although popular, lacked definitive experimental confirmation and left numerous questions unanswered. Was the positive charge distributed evenly across the atom? How were the electrons positioned? What force ensured the atom's stability? In 1909, Ernest Rutherford, a physicist from New Zealand based at the University of Manchester, set out to probe these questions. A passionate investigator of atomic behavior, Rutherford, along with his students Hans Geiger and Ernest Marsden, developed an elegantly simple but revolutionary experiment that would forever reshape atomic theory. The experimental setup was straightforward yet clever. Rutherford and his team directed a focused stream of positively charged particles, known as alpha particles, at an extremely thin sheet of gold foil. Alpha particles, made up of 2 protons and 2 neutrons, carry a positive charge and have significantly more mass than electrons. These particles were chosen because their high energy and penetrating power made them ideal for probing atomic interiors. Based on Thomson's model, the alpha particles were expected to travel through the gold foil with barely any deflection, perhaps veering slightly due to the weakly distributed positive charge. To track the alpha particles, Rutherford's team employed a circular screen coated with zinc sulfide, a material that emitted tiny flashes of light whenever struck by an alpha particle. By analyzing these scintillations, the scientists could trace the trajectories of the particles as they moved through or bounced off the gold foil. What they observed was both shocking and confusing. As predicted, most alpha particles sailed through the foil with little to no deviation, but unexpectedly a small fraction were deflected at large angles, and some even rebounded nearly directly back toward their source. This startling result defied the predictions of the plum pudding model. Rutherford himself was astonished. He famously compared the finding to firing a 15-inch shell at a piece of tissue paper, only for the shell to bounce straight back. Such dramatic deflections couldn't be explained by a diffuse cloud of positive charge. Something much more concentrated and forceful had to be hidden within the atom. Through careful analysis, Rutherford proposed a bold new idea. The atom's positive charge, and nearly all of its mass, was not spread evenly, but instead focused in an incredibly small, dense, central region. He called this compact core the nucleus. According to this new nuclear model, the electrons were not embedded inside a positive mass, but instead orbited around the nucleus, leaving most of the atom as empty space. This concept was revolutionary. Instead of a soft sphere of positive matter, the atom now resembled a miniature solar system with a dense central nucleus and orbiting electrons. The nuclear model not only accounted for the experimental data, including the unexpected deflections, but also introduced a coherent structure for atomic organization. Rutherford's insights formed the basis of the planetary model of the atom, where electrons revolve around a central nucleus, much like planets circle the sun. This refined view of atomic structure would soon inspire Niels Bohr to develop his own atomic model, introducing the concept of quantized electron orbits to explain atomic stability in greater detail. Beyond shaping atomic theory, Rutherford's discoveries laid the foundation for the entire field of nuclear physics. In 1917, he achieved another historic breakthrough, becoming the first scientist to split the atom, uncovering the proton as a fundamental component of the nucleus. Rutherford's model didn't just provide answers, it fundamentally changed our perception of matter. The idea that atoms are composed mostly of empty space was a paradigm shift. It meant that the solidity we perceive in everyday objects arises not from densely packed particles, but from electromagnetic forces at the atomic level. This insight would later influence the development of quantum mechanics, as researchers worked to understand the underlying forces governing subatomic particles. Looking back, the gold foil experiment appears remarkably simple, but the knowledge it produced was profound. Rutherford's work dismantled a dominant theory and uncovered the true architecture of the atom. His discovery of the nucleus didn't merely update scientific thinking, it revolutionized it, shaping future research in chemistry, physics, and beyond. The experiment also stands as a model of scientific inquiry. With a meticulously designed test, Rutherford challenged deeply held assumptions and welcomed unexpected results with intellectual openness. His approach demonstrated how experimental evidence, when carefully gathered and thoughtfully interpreted, can lead to a complete rethinking of scientific understanding. In the end, Rutherford's legacy is one of bold curiosity and rigorous investigation. What began as a straightforward experiment evolved into a monumental scientific breakthrough, answering foundational questions about the nature of matter. His pioneering work continues to influence the way we explore and understand the atomic world. Tracing the origins of the electron, a revolutionary breakthrough in physics. In the latter part of the 19th century, the scientific world was approaching one of the most transformative discoveries in the realm of physics: the electron. Prior to its revelation, the inner workings of the atom remained a profound mystery. Many believed atoms were indivisible units, the smallest possible constituents of matter. This idea had ancient roots, going back to Greek thinkers like Democritus, who coined the term atomos, meaning uncuttable or indivisible. However, as experimental science advanced, researchers began to gather evidence suggesting that atoms were far more intricate than previously thought. The discovery of the electron would become a key milestone in decoding that complexity. This monumental finding emerged from investigations involving cathode rays. By the mid-1800s, scientists had grown increasingly interested in a strange occurrence observed in partially evacuated glass tubes. When an electric current was applied between two electrodes inside the tube, a mysterious glow would appear. These glowing streaks, termed cathode rays, appeared to originate from the cathode, the negatively charged electrode. and travel toward the anode, the positively charged electrode. The true nature of these rays was unclear. Were they waves, like light, or streams of tiny particles? Throughout the late 1800s, numerous experiments revealed that cathode rays could be bent or deflected by both magnetic and electric fields. This behavior suggested that they behaved more like particles, yet the scientific community was divided. Some insisted cathode rays were a new type of wave, while others argued they consisted of material particles. The person who finally settled the debate was English physicist J. Thomson. In 1897, at the Cavendish Laboratory in Cambridge, Thomson conducted a series of detailed experiments to examine cathode rays more closely. He wanted to determine whether these rays were truly composed of particles, and if so, what their properties might be. Using a specially designed cathode ray tube, Thomson applied both electric and magnetic fields to the rays. By adjusting the strength of these fields until their opposing effects on the ray neutralized each other, he was able to precisely measure how much the rays bent under each force. This allowed him to calculate the charge-to-mass ratio of the ray's particles. The results were staggering. Thomson discovered that the particles in the rays were nearly 1,800 times lighter than a hydrogen atom, the lightest known element. This finding was unprecedented. Until then, scientists had no idea particles smaller than atoms could exist. Thomson concluded that cathode rays were made up of tiny particles, far smaller than any atom, and that these particles carried a negative electric charge. This groundbreaking realization overturned the age-old notion that atoms were indivisible. Not only had Thomson shown that atoms could be broken down into smaller components, but he had also identified the first known subatomic particle, which he named the electron. To account for his discovery, Thomson proposed a new model of the atom. Since he had found negatively charged electrons, he reasoned that atoms must also include positive charge to counterbalance the negative. This led to the development of the plum pudding model, in which the atom was imagined as a positively charged substance with negatively charged electrons scattered throughout, like raisins suspended in pudding. Although later discoveries would render this model obsolete, it represented a crucial leap forward in understanding atomic structure. The implications of the electron's discovery were both immediate and far-reaching. By revealing that atoms contained even smaller components, Thomson opened the door to the field of subatomic physics. This new knowledge forced scientists to reconsider the nature of matter itself. Questions quickly emerged. Where exactly was the positive charge located within the atom? How were electrons arranged? And what forces held them in place? Thomson's work lit the path for the next generation of physicists. The quest to understand atomic structure became central to modern physics. It directly influenced the experiments of Ernest Rutherford, who later discovered the atomic nucleus, and Niels Bohr, who introduced a quantum-based model explaining electron behavior and atomic stability. Moreover, the discovery of the electron didn't just transform theory, it launched an entirely new field, electronics. The understanding of how electrons move and interact led to the invention of critical technologies such as semiconductors, transistors, and eventually computers. Today, nearly every technological device, from smartphones to MRI machines, relies on principles that stem directly from Thomson's early experiments with cathode rays. Looking back on the electron's discovery, it's extraordinary to consider how a single breakthrough reshaped both science and society. Thomson's rigorous and methodical experimentation demonstrated how observation, paired with a willingness to question established beliefs, could redefine humanity's view of the universe. The discovery of the electron is now recognized as the foundational moment in quantum theory and modern atomic science. It set the stage for some of the most significant scientific advancements of the 20th and 21st centuries. In many respects, Thomson embodied the essence of scientific inquiry. He took a seemingly simple phenomenon, a glowing light in a glass tube, and followed it to its deepest implications, even when it went against the prevailing wisdom of his time. Today, every flick of a light switch, every email sent, and every digital device used owes its functionality to the understanding of the electron, an understanding made possible by Thomson's relentless pursuit of truth. Through his discovery, J.J. Thomson didn't merely identify a new component of matter, he fundamentally reshaped our conception of reality and laid the foundation for the atomic era, revolutionizing space and time, the rise of relativity. As the 20th century dawned, science began to challenge the foundational principles that had underpinned physics for centuries. For generations, Isaac Newton's laws had provided the definitive explanation for motion, gravity, and the workings of the universe. Yet, as researchers delved deeper into the mysteries of the cosmos, they encountered anomalies that Newtonian mechanics couldn't fully explain. At the heart of this scientific upheaval stood Albert Einstein, the physicist who would fundamentally reshape our understanding of space and time. Before Einstein's arrival, the dominant scientific worldview was based on Newton's descriptions of a universe governed by consistent, unchanging rules. In this model, space was perceived as a fixed, immovable backdrop, and time was assumed to tick uniformly for all observers. This elegant system had long appeared complete. However, cracks in this framework began to appear in the late 19th and early 20th centuries, particularly in relation to the behavior of light. In 1865, Scottish physicist James Clerk Maxwell developed equations that explained electromagnetic waves, including light, as oscillating electric and magnetic fields that could sustain each other and travel through space. Crucially, Maxwell's work implied that light always moved at a constant speed of approximately 299,792,458 meters per second. Yet attempts to measure the speed of light relative to a theoretical substance called the ether, once believed to be the medium carrying light waves, had consistently failed. These experiments showed that light's speed remained unchanged regardless of the Earth's motion, a result that baffled scientists and threatened the structure of classical physics. This is where Albert Einstein, born in 1879, entered the scene. Known for his unconventional thinking and deep reliance on thought experiments, Einstein was captivated by the enigmatic nature of light and the unresolved problem of the ether. Rather than accept outdated notions or adhere strictly to Newtonian theory, Einstein posed a radical question. What if space and time weren't rigid or absolute? What if they could bend, compress, or stretch, depending on the observer and conditions in the universe? From this idea emerged a revolutionary concept, special relativity, which Einstein introduced in 1905 at just 26 years old through his paper titled On the Electrodynamics of Moving Bodies. In this landmark work, Einstein presented two fundamental postulates. One, the laws of physics are identical for all observers, regardless of their constant velocity. Whether someone is at rest, walking, or riding a high-speed train, the core physical laws remain unchanged. 2. The speed of light is the same for all observers, no matter how fast they are moving in relation to the source of the light. This second idea was especially shocking. Under Newtonian assumptions, we'd expect someone moving toward a light source to measure light as faster than someone moving away. But Einstein insisted that light's speed doesn't vary. It remains constant for everyone, regardless of their motion. These ideas had extraordinary implications. Space and time were no longer fixed realities. Instead, they were relative and interconnected. Einstein's theory introduced a new concept, space-time, a four-dimensional continuum that merges the three dimensions of space, length, width, and height, with the dimension of time. This fusion drastically altered our understanding of the cosmos.
One of the key outcomes of special relativity was the concept of time dilation, the idea that time slows down for objects moving near the speed of light. For instance, a person traveling on a spaceship at 99% the speed of light might experience 1 year of travel, while many more years pass on Earth. The faster one moves, the slower time flows for them compared to stationary observers. Another important result was length contraction. As an object approaches light speed, it appears to shrink in the direction of its motion when viewed from a stationary frame. So, an astronaut traveling at near light speeds might see a ruler or a stick appear shorter compared to what it looks like on Earth. But Einstein's work didn't stop there. In 1915, he expanded his theory to include gravity, giving rise to general relativity. While special relativity dealt with constant speeds and motion, general relativity explained how gravity works in a new and deeper way. Previously, Newton had described gravity as a force acting between two masses. Einstein reimagined gravity as the curvature of space-time caused by mass and energy. He asked us to picture the universe like a stretched rubber sheet. If a heavy object, like a planet or star, sits on the sheet, it causes a dip in the fabric. Smaller objects nearby then move along the curves of that dip, what we perceive as gravitational attraction.
In this view, gravity wasn't a pull between objects, but rather the bending of space-time itself. This revolutionary perspective completely redefined one of nature's most familiar forces. Einstein's theories didn't remain speculative for long. In 1919, during a solar eclipse, British astronomer Arthur Eddington observed the bending of starlight around the sun, an effect Einstein's theory had predicted. The results matched precisely, catapulting Einstein to international fame and validating general relativity. Today, the theory of relativity stands as a cornerstone of modern physics. Technologies like GPS rely on it. Without accounting for time dilation effects from both speed and gravity, GPS signals would become inaccurate. From satellite systems to cosmic models, Einstein's insights permeate every layer of modern science and technology. The impact of relativity went far beyond equations. It reshaped how humanity thinks about time, space, and the fabric of reality itself. It revealed a universe that is far more intricate and surprising than previously imagined, and opened the door to discoveries that continue to transform our world. Einstein's work on relativity didn't merely revise old theories, it fundamentally changed our perception of the universe, leaving a legacy that continues to inspire and challenge scientists to this day. Unlocking light's mystery, the quantum leap of the photoelectric effect. The photoelectric effect stands as a fundamental pillar in the foundation of quantum theory. It represents a turning point in the quest to understand the peculiar and non-intuitive behavior of particles at the atomic and subatomic levels. At the beginning of the 20th century, physicists found themselves confronted with phenomena that refused to conform to the principles of classical physics. One such mystery was how light interacting with metal surfaces could cause the release of electrons, an event that didn't align with the prevailing understanding of light's behavior. That enigma would be solved by Albert Einstein, whose insights into the photoelectric effect not only resolved this anomaly, but also paved the way for the rise of quantum mechanics. To appreciate why the photoelectric effect was such a breakthrough, it's essential to grasp the scientific context of that era. During the 1800s, the wave theory of light dominated. This view was supported by James Clerk Maxwell, who formulated equations showing that light was an electromagnetic wave moving through space as intertwined electric and magnetic fields oscillating together. This wave-based model successfully explained many phenomena, from diffraction and interference patterns to the vibrant colors in a rainbow. But confusion arose when scientists observed something unexpected during experiments with metal surfaces. When light of a specific frequency struck a piece of metal, electrons were released from its surface, a process named the photoelectric effect. According to classical theory, this should have been straightforward. The wave model suggested that increasing the intensity, or brightness, of the light would also increase its energy. Therefore, brighter light, regardless of its frequency, should have easily knocked electrons loose. But the results told a different story. Surprisingly, the energy of the ejected electrons didn't correlate with how bright the light was. Instead, only light above a certain frequency threshold could dislodge electrons. Once that frequency was exceeded, brighter light would emit more energetic electrons, but only if the frequency was high enough. This completely defied expectations. If light behaved purely as a wave, why would the frequency be more important than the intensity? This puzzling contradiction is where Einstein made his mark. In 1905, Einstein published a paper that would reshape physics forever. In it, he proposed a bold new concept. Light wasn't only a wave, it could also act like a stream of particles. These particles of light, which he initially called quanta, later renamed photons, carried energy directly tied to their frequency. Einstein theorized that when light hits a metal surface, it's these individual photons, not the entire wave, that transfer energy to electrons. If a single photon possesses enough energy, which depends on its frequency, it can knock an electron out of the metal. If the photon's frequency is too low, it lacks the energy to release an electron, regardless of how intense or bright the light is. In the classical wave model, the intensity of light is related to the wave's amplitude. A bigger wave should carry more energy and eject more electrons. But Einstein flipped this logic. In his particle model, what mattered was not the overall brightness, but how much energy each photon carried. Thus, even an intense beam of low-frequency light, like infrared, wouldn't free electrons, because its photons didn't have enough punch. Only high-frequency light, like ultraviolet, carried photons with sufficient energy to eject electrons from the metal. This breakthrough was a cornerstone in the development of quantum theory. It revealed that energy, light, and matter were intertwined in ways that classical physics couldn't explain. It also introduced the principle of wave-particle duality, the idea that light could exhibit both wave-like and particle-like behavior depending on the situation. Einstein's explanation was revolutionary, but it wasn't embraced right away. Many scientists struggled to accept that light could behave both as a wave and a particle, as it contradicted centuries of conventional wisdom. Nevertheless, experimental evidence steadily confirmed his theory. Repeated tests demonstrated the quantized nature of light, and in 1921, Einstein was awarded the Nobel Prize in Physics for his explanation of the photoelectric effect, not for his more famous work on relativity. This discovery reshaped our understanding of energy. It validated the idea that energy comes in discrete packets, not as a smooth and continuous flow. This notion of quantized energy would later be extended to describe atoms, electrons, and all subatomic behavior, becoming central to quantum physics. Beyond theory, the photoelectric effect also sparked real-world applications. Technologies like solar panels, which turn sunlight into electricity, photodetectors, and light sensors all function thanks to the interaction of light and matter described by Einstein. The photoelectric effect wasn't just a scientific curiosity, it was a crucial insight that unlocked the inner workings of light and matter. It became a vital step in building a framework for understanding quantum behavior, revealing that at the smallest scales, the universe doesn't obey the same rules we observe in daily life. Einstein's work remains one of the most influential contributions to modern physics, showing us that light isn't just a wave, but also a particle. It helped introduce a quantum reality where the old laws no longer applied, and where time, space, and energy take on new and surprising forms. In many ways, the photoelectric effect is like a gateway into the quantum realm, a place where particles behave like waves. Energy comes in tiny packets, and our traditional understanding of nature begins to unravel. And it all started with a deceptively simple question. What is light, really? That question, and the search for its answer, continues to guide and transform our understanding of the universe to this day. The quantum breakthrough, a new frontier in physics. In the early 20th century, physicists found themselves at the edge of a scientific revolution. While classical physics, with its elegant laws of motion, gravity, and electromagnetism, had explained the physical world remarkably well, it began to falter as scientists explored the behavior of matter at extremely small scales. As they delved deeper into the microscopic domain, matter no longer followed the predictable patterns described by traditional physics. Particles within atoms and molecules began behaving in ways that were totally unfamiliar. Rather than moving in clear, defined paths, they seemed to fluctuate within a strange, probabilistic reality governed by new and unfamiliar principles. This strange and fascinating field would come to be known as quantum mechanics. The groundwork for quantum mechanics was laid during the late 19th century, particularly through the study of black-body radiation. Scientists aimed to understand how hot objects, like heated metal rods, emitted electromagnetic radiation. Classical theories predicted that these objects would release infinite amounts of energy across a continuous range of wavelengths. However, experiments showed that only specific wavelengths were emitted, and the energy released at each was sharply limited. This contradiction became known as the ultraviolet catastrophe, and classical theory had no solution. Then in 1900, German physicist Max Planck introduced a groundbreaking proposal. Energy was not emitted continuously, but in small, discrete units, which he called quanta. This marked the first major blow to the classical framework. Planck's idea introduced the concept of energy quantization, the idea that, at a microscopic level, energy exists only in specific amounts. While Planck's theory elegantly resolved the black-body radiation paradox, many saw it merely as a mathematical workaround, not a fundamental change in the understanding of reality. But just 5 years later, in 1905, Albert Einstein extended Planck's idea even further. In his study of the photoelectric effect, Einstein proposed that light, long regarded as a wave, also behaved like a stream of particles. He argued that light was made up of energy packets called photons. When these photons hit a material, they could transfer energy to electrons, knocking them out of the surface, much like a ball hitting and dislodging another object. Einstein's theory demonstrated that light could act as both a wave and a particle depending on how it was observed. This dual behavior became known as wave-particle duality. His explanation of the photoelectric effect earned him the 1921 Nobel Prize in Physics and solidified the early foundations of quantum theory. However, the strangeness wasn't limited to light. By the 1920s, physicists discovered that atoms themselves did not conform to classical descriptions either. The model of the atom as tiny solid spheres orbiting the nucleus in well-defined paths was quickly falling apart. In 1913, Niels Bohr introduced a revolutionary atomic model. He proposed that electrons revolve around the nucleus at specific quantized distances and could gain or lose energy only by jumping between these levels. This helped explain why atoms emit light at specific wavelengths, and it hinted that matter, too, followed quantum rules. Quantum mechanics truly took shape in the mid-1920s, thanks to pioneering physicists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, who developed the formal structure of the theory. In 1925, Heisenberg introduced matrix mechanics, a new mathematical approach that described particle behavior through observable quantities like position and momentum. Although powerful, this method lacked a visual model of what was happening. Then in 1926, Schrödinger introduced his famous wave equation, proposing that particles such as electrons could be described as waves rather than point-like objects. His equation didn't provide exact predictions, but it allowed scientists to calculate the probability of finding a particle in a specific place, a revolutionary idea. At the heart of quantum mechanics was a surprising insight. Particles do not have definite positions or speeds until they are measured. Instead, they exist in a superposition, a blend of all possible states, described by a wave of probability. Once measured, this wave collapses, and the particle is observed in one specific state. This uncertainty was formally captured by Heisenberg's uncertainty principle, which declared that we cannot simultaneously know a particle's position and momentum with perfect accuracy. The more precisely one is known, the less certain the other becomes. Quantum mechanics unveiled a world unlike anything we can perceive directly. On this tiny scale, particles exist in overlapping states, can become instantaneously linked across distances, entanglement, and move in ways that defy classical logic. Most remarkably, these bizarre results weren't due to faulty equipment or incomplete theory. They reflected the true nature of reality. Quantum mechanics showed that, at the smallest scales, the familiar rules of the macroscopic world, determinism, continuity, and certainty, no longer apply. Instead, probability and indeterminacy are fundamental. This quantum view introduced mind-bending ideas like wave-particle duality, superposition, and entanglement, concepts that defy our everyday understanding of how nature works. Despite its strangeness, quantum mechanics is one of the most accurate and successful theories in science. It has enabled the creation of countless technologies, from transistors and lasers to the very computers and smartphones we rely on today. But quantum theory also raised deep philosophical questions. If particles can exist in many states, what determines the state they choose when measured? If particles are entangled, does that mean information can travel faster than light? These puzzles continue to challenge scientists and philosophers alike. But one truth remains. Quantum mechanics has fundamentally transformed how we understand the universe. It's more than just a set of equations. It's a profound new perspective on what reality is. To conclude, quantum mechanics is a triumph of modern science. It has passed countless experimental tests, and its consequences still ripple through technology and theory alike. Even though the quantum world seems alien and incomprehensible, it follows well-defined principles that govern everything from the tiniest particles to the vastness of the cosmos. Ultimately, quantum mechanics is the instruction manual of the universe at its most fundamental level. The principle of uncertainty, a quantum shift in perception. Imagine standing at a concert, intent on capturing the perfect image of a musician mid-performance. You carefully line up your shot, but just as you press the shutter button, the performer shifts unexpectedly. The result? A blurred photo where the movement is unclear. Now picture a different scenario, zooming out to photograph the entire stage. This time, the image might be sharp and still, but the fine detail of the musician's motion is gone. The clearer you make one aspect, motion or location, the more you lose clarity in the other. This experience mirrors one of the most fundamental ideas in quantum physics, Heisenberg's uncertainty principle. Much like in photography, where focusing on one element sacrifices the clarity of another, subatomic particles, such as electrons, cannot have both their position and momentum precisely determined at once. No matter how refined or powerful our tools become, this isn't a technological limitation. It's a basic feature of nature itself. Werner Heisenberg introduced this principle in 1927, turning conventional ideas of measurement and observation on their head, particularly at the microscopic scale. To understand how this groundbreaking idea emerged, we must rewind to the 1920s, a decade where quantum mechanics was rapidly evolving. Pioneers like Niels Bohr, Erwin Schrödinger, and Heisenberg were laying the groundwork for this revolutionary framework. In this emerging view, particles such as electrons were not tiny solid objects, but quantum waves, existing as clouds of probabilities, not fixed points. These subatomic entities could behave as both waves and particles, depending on how they were measured, an unsettling realization that upended classical physics. Heisenberg, grappling with this duality, searched for a consistent way to understand how particles and waves interacted. His breakthrough came while studying how light interacted with electrons, especially inside atoms. The more accurately scientists tried to pinpoint an electron's location, the less certain they became about its momentum, how fast it was moving, and in which direction. The reverse was also true. From this, Heisenberg proposed a foundational truth. There is a natural boundary to how precisely we can measure certain pairs of physical properties at the same time. This insight gave rise to the uncertainty principle. In simple terms, the more exact we are about a particle's location, the fuzzier our knowledge of its momentum becomes, and vice versa. Far from being a philosophical musing, Heisenberg's principle had a mathematical basis. It is described by an equation that quantifies the relationship between uncertainty in position and uncertainty in momentum. The precision of one necessarily increases the imprecision of the other. At first glance, this may seem like a flaw in measurement, an experimental error. But Heisenberg's insight went far deeper. The uncertainty was not due to the shortcomings of our instruments, but was instead a fundamental property of the universe at the quantum level. In other words, the unpredictability is not artificial, it's built into reality. Before this, classical physics rested on the foundation of determinism, the belief that given enough information about a particle's current position and speed, we could predict its future with total accuracy. This worldview brought comfort and order, explaining everything from planetary motion to baseball trajectories. But in the quantum domain, Heisenberg's principle completely disrupted this neat predictability. Suddenly, we could no longer speak of particles following a definite path through space. Instead, we had to adopt a new approach. Quantum theory is probabilistic, not deterministic. Subatomic particles exist not in one defined state, but in a range of probabilities, only taking on specific values when observed. And this uncertainty was not due to a lack of knowledge. It was intrinsic to the quantum world. The implications weren't limited to physics. They sparked philosophical debates about the very nature of reality and what it means to know something. Could we ever completely understand a system, its location, speed, energy, and so on? According to Heisenberg, we could not. This forced a major shift in how scientists viewed measurement. In classical terms, measuring a system meant simply looking at it without affecting it. But quantum mechanics revealed that the act of measuring changes the system. An electron's wave-like behavior collapses into a specific location or momentum only when it is measured, and that process eliminates all other possibilities. This view evolved into the Copenhagen interpretation, promoted by Bohr and Heisenberg. According to this interpretation, quantum reality is not determined until we observe it. Until then, particles exist in a superposition, a blend of every possible state. Observation forces them to choose one outcome, but because of the uncertainty principle, this choice comes with a trade-off. Gain precision in one property, and you sacrifice it in another. Although the uncertainty principle might seem abstract or unrelated to everyday life, its impact is enormous. One key example is quantum tunneling, where particles pass through barriers they shouldn't be able to cross according to classical physics. This phenomenon powers crucial technologies like semiconductors and MRI machines. In semiconductors, electrons behave in ways governed by the uncertainty principle. This behavior makes modern electronics, including computers and smartphones, possible. Even though the principle challenges our intuitive grasp of reality, it has been verified countless times through rigorous experimentation. It is one of the cornerstones of quantum theory, profoundly influencing not just technology but also how we interpret the nature of existence. Heisenberg's principle showed us that limits on knowledge are not flaws, but features of the universe's most basic structure. The uncertainty principle doesn't just reshape our ideas about particles and waves, it redefines what we can ever know about the universe. It draws a boundary around certainty and tells us that some mysteries may never be solved with exactitude. As technology progresses and quantum science continues to advance, the uncertainty principle remains central to our understanding of the cosmos. It teaches us that even within the unknowable, there is structure, elegance, and meaning. In embracing uncertainty, we gain new insight that truth can exist even without full clarity, and some of the most profound discoveries are found not in what we know, but in the questions we learn to ask.